When you compare two nearly identical sequences that have fallen slightly out of sync, the result often looks like total chaos. Standard version control scripts struggle with a specific vulnerability. They check line 1 against line 1 and line 2 against line 2. If you insert a single new line of code at the top of a document, every subsequent line shifts down. The script sees those offset lines and reports that you deleted the entire file and rewrote it from scratch. Searching for exact substrings, the identical, unbroken blocks of text, is insufficient for code. Code edits are rarely contiguous. We add variables in one place and delete functions in another. There are gaps. We need to track the relative order of the code. The system must build a bridge over those gaps and misaligned sections while strictly maintaining the sequence. Tools like Git handle these shifts by identifying the exact insertions and deletions without being confused by the change in line numbers. This logic is powered by a mathematical framework known as the Longest Common Subsequence, or LCS. To find the LCS, we place the tokens of the original file on the x-axis and the edited file on the y-axis, forming a grid. We establish the boundaries of the algorithm by setting the first row and the first column to 0. From here, the algorithm follows a match rule. When the code tokens on the x and y-axis are identical, we have a link in the chain. The algorithm looks at the score in the top left diagonal cell and carries it forward, +1. If the tokens are a mismatch, the algorithm has to choose between two historical paths. It checks the cell immediately above and the cell immediately to its left, then permanently adopts the highest historical value between them. These two rules, adding for matches and carrying the maximum for mismatches, cascade until the entire grid is populated. The number in the final bottom right cell represents the definitive length of the shared history between the two files. Having the total length of the shared sequence doesn't explain how the terminal actually displays those red and green highlights. To generate that readout, we start a traceback. We walk the optimal path backward from the finish line toward the start. Every time the path moves diagonally, it represents code that didn't change. We keep that line in neutral gray. A horizontal jump indicates a line present in the original file but missing in the new one. That is a deletion. A vertical jump means a line exists in the new file that wasn't in the original, and insertion. This reverse-engineered coordinate map is the actual engine generating the edit scripts and diffs we use every day. This becomes a problem of scale. Comparing two files with 10,000 lines of code each creates a matrix with 100 million cells. Storing that entire matrix takes up a massive amount of memory. In computer science terms, this is O of m times n space complexity, which can easily crash system RAM when parsing large repositories. The algorithm reveals a shortcut. To calculate any row, the system only needs the row immediately above. Discarding the history, we keep only 2 active rows. Going further, a rolling state merges these into a single 1G array, continuously overwriting itself. Compressing space complexity to a linear scale is why version control systems compare massive source repositories or align DNA sequences without exhausting the hardware.